welcome everyone to Cadet Brian Hill thesis presentation. Brian's been working with me since he was a rat, frankly, and last summer he had an internship, I guess, at NASA Langley in Hampton, Virginia. And due to that internship, he found a very good topic for his thesis, and it's called an investigation of IoT protocols for the enhancement of performance and security. So, have at it.
So, good morning, everyone. Today we'll go through the introduction to the problem, the goal that we had throughout this project, as well as some terminology with those sheets that I've handed out to everybody. For those of you that just walked in, they're available on the table over there. And the methodology that we used to approach this problem, as well as the revisions that we made along the way. We'll go into the final results, a cost and security analysis, and then some of the work that can be done on this project in the future, and we'll have questions at the end. So, what is the Internet of Things? It's defined as interrelated data gathering, control, and computing devices that are able to send data over a network without requiring human interaction. However, due to the high degree of interconnectivity of these devices, they become a channel for cyber attacks. For example, in 2016, the Miari botnet was able to crash huge parts of the internet by exploiting flaws in IoT devices such as closed-circuit TV cameras. So you may be wondering why these devices are so inherently unsecure. Part of it is that consumers just don't really have the adequate knowledge to be able to determine whether or not the product that they own is really secure or not. From a producer or company's point of view, the profits are highest when companies that produce the devices can quickly get them available for sale and off of the shelf. Investing in security for these devices can slow down the rollout process, and it's often just pretty much overlooked. These devices not only offer vulnerability for themselves, but sometimes provide a backdoor into bigger networks such as the home or the office. In addition, the consumers themselves sometimes pose a security threat. For example, with that botnet, many of the cameras that were taken over because they weren't properly set up and password protected. And that's something that also has to be accounted for. So, an issue that's widely discussed in a lot of publications about the Internet of Things and security is the lack of standardization that exists between these devices. It makes it much harder to address security when you're dealing with a wide variety of different devices. So there are four primary choices, essentially, and four routes that you can go to try and enable security throughout the Internet of Things. And the first would be a large-scale behavior of the standard protocols and behavior of the Internet. However, there isn't really one party that could do this. There's not a large lack of interest, and there would be a huge cost involved. So this would be extremely unlikely. Secondly, there could be legislation from the government that would mandate better practices for the producers of these devices. However, it's unlikely that this would receive bipartisan support. The government's slow, and with other issues at hand, it's unlikely that this would even be an issue that was surfaced to the public. Thirdly, all these companies could simply start to produce devices that have more of a focus on security, but they don't really have any incentive, and for the same reasons I listed before, I believe that this is extremely unlikely as well. So the last route that can be taken is implementing security through third-party methods. So a lot of companies would be more incentivized that use IoT devices to enable them through third-party methods because it would help them secure their data. This method would reduce the reliance on the security of individual devices themselves and would place an emphasis on network security, such in the way that we've done in this project. So as with most network security issues, it must be addressed in layers. One proposed architecture to the Internet of Things includes the application layer, support layer, sensor layer, perceptual network support layer, and application layer. And each of these sites presents unique challenges from the last. So the perceptual layer consists of the different sensor technologies. It can be exposed to threats such as spoofing, which is pretending to be a known source of data, eavesdropping, or even radio frequency jamming. The network layer consists of all wireless sensors where the integrity of a single node can compromise the integrity of the entire network. The support layer includes the data storage technologies where unauthorized access or even malicious insiders can tamper with data. The application layer is what is called a user useful layer, where you can see things such as a smart home or smart car, where you have to worry about issues such as network sniffing or malicious code injection. So as Colonel Livingston said, the reason all these slides are NASA themed, I started this project back in May of 2018 with a grant with my mentor from the Research Center in Hampton, Virginia. And the original goal of this project was to enable webbing-enabled microcontrollers to securely transmit data and address both the physical and network security. In addition, we wanted to be able to use lightweight technologies in a low power consumption environment so that these individual microcontrollers could be used for long periods of time off of battery power. An example of one of the applications of this is we had another worker come and talk to us at NASA Langley who had a pipe running through a warehouse, and they had had issues in the past where the pressure in the pipe would become too high, and I believe that it had even burst on occasion. So the temporary solution was they had to have someone go by and check this pipe consistently to make sure that the pressure wasn't too high. And the only way of doing this was to actually climb up a ladder up in the ceiling and look at an analog dial that would read off the pressure of the pipe. Now what this person wanted to do is put a wireless sensor on the pipe that would be able to keep track of that data, send alerts via email and text, and have some kind of time series dashboard so that he could look from another computer and make sure that it wasn't behaving out of the ordinary and they wouldn't have that risk of the pipe bursting again. So one problem is that obviously NASA is a government organization and they have very strict protocols about how their sensitive data is handled. And even though something like the pressure in the pipe might not seem like it should be sensitive data, there is a baseline level of security that they have to have for any kind of data on the research center. So we couldn't do this without having that secure network that we could transmit that data and make sure that it wasn't taken by a third party. So there are many other useful applications for this platform. For example, you can control access to resources by using an RFID scanner. I believe that this platform would help NASA with their long-time goal of becoming a smart center by enabling the use of wireless technology all over the center. You can use these sensors to monitor the temperature and air quality in the smart labs or sanitary environments. And all types of different sensors can be implemented. Vibration sensors on machinery to make sure that the machine is behaving the way that it should, GPS and movement tracking, power consumption analysis, and more. All of the data collected can be used to help machine learning algorithms, which are powered by large sources of data. And another project being implemented at NASA Langley involved the use of drones and fleet technology, and this type of network would help these drones communicate with one another without the risk of the code being taken by a third party. So to control all these sensors, we chose a device called the ESP32. The ESP32, as you can see on your sheet, is a web-enabled microcontroller, and the role of the device in this network is for it to collect and transmit data. The reason we chose this specific board is they cost about $20. They can run off battery power for very long periods of time. They support Wi-Fi and Bluetooth, which is a necessity for web-enabled applications. You can apply updates over the air to one or many devices at once, which is very useful if you have devices in hard-to-reach places. And they can also be physically secured to a higher degree than many other out-of-the-box products, which I'll touch on a little more later. So I'll run through some of the terminology real quick that everyone got on their sheets. As I just said, the ESP32 is that internet-enabled microcontroller that collects and transmits data to the cloud. Amazon Web Services is a secure cloud services program that offers compute power, database storage, and other functionality. We chose this because it's cheap and it allows automation of processes. Message Queuing Telemetry Transport, or MQTT, is the protocol that our microcontroller uses to transmit data. It's a standard protocol for IoT devices that uses a publish and subscribe method of data transmission. JavaScript Object Notation is a lightweight data format that's easy for computers and humans to read and write. Transport Layer Security is a standard practice for securing web traffic using cryptographic protocols such as data encryption and authentication from devices. AWS IoT Core is the broker that enables interaction between our ESP32s and applications in the cloud. AWS Lambda is a serverless computing service, and in our application, it's used to send that JSON data to a virtual server. Hypertext Transfer Protocol Secure, or HTTPS, is a standard protocol for nearly all secure web communication, and it's also based off of Transport Layer Security. Amazon Elastic Compute Cloud is a virtual and scalable server. Kinesis Firehose is a service that allows you to transmit large amounts of data. S3 is an Amazon Web Services database in a file explorer format that looks similar to what you might see on your PC or Mac. QuickSight is an AWS service to visualize data. And InfluxDB and Grafana are both open source pieces of software. They're both designed to be used for IoT implementations, where InfluxDB is a database and Grafana is used for dashboarding data. So now I'll walk through what the original methodology was with the project. So the first thing we did was we developed almost entirely on Amazon Web Services. We did this because it's cheap, it's easy, and it's scalable, which is very important because it helps the ability to add or remove many devices at once. In this implementation, we collect data with the microcontroller and we send it to IoT Core, that broker that I talked about. And then next, it's sent through the Kinesis Firehose, which is simply just a method of transmitting large amounts of data. We use QuickSight to visualize the data at the end. It's also important to note that throughout this project, we are running a real-time operating system on the ESP32. To put simply, that means that we can quickly process all the data that is coming through all the sensors. So what you're seeing here are the rules that determine how that broker handles the data that's coming through. So this is the IoT Core dashboard. It's not only responsible for data collection and security of transmission, but it's also responsible for transferring that data to the other services in Amazon Web Services. The user creates rules here that determine one or more actions to perform based on the data that's coming through in a message format. The devices are communicating via MQTT. As I said before, that's a publish and subscribe pattern. Here, we have demo BL53 is the channel that the IoT broker is reading. So any individual device or the broker can publish or subscribe to certain channels. This enables interaction between the devices and the broker, between two different devices, and also allows us to update the devices over the air. The rest of what you're seeing here, select and an asterisk, means that we're reading all data from that channel. The next portion of that line is simply just adding a timestamp so we know at what time all those pieces of data are coming through. The rules below determine what will happen with the data after it's sent through IoT Core. So as you can see, this sends it to the Kinesis Firehose and to the database here, where it's then dashboarded. So here's an example of the database that we were originally using. This is Amazon S3. As you can see, it kind of looks similar to something you might see on a Mac or a PC, just a normal standard file explorer. It's great for looking at as a person, however, we found that it didn't work very well for a computer to parse through this data, so we ended up replacing this database later on. Below, right here, is an example of what's being held in one of these files. It includes the label here, the actual value for that distance, and the timestamp that we added before. This is exactly what's being sent from the microcontroller and added by the IoT broker. So this is originally how we had dashboarded the data. As you can see, it just doesn't look very pretty. So this is, again, the Amazon QuickSight service. We also found that this service is not yet tailored to work well with time series data, so we ended up replacing this service and using a third party as well. So this is a diagram of the refined system methodology that I'll walk you through real quick. Here we have the sensors that are feeding to those ESP32s, those web-enabled microcontrollers. From there, the device sends that data via MQTT to the cloud. At this point, the data is entirely in the cloud. It's being handled by that same broker. And what we did, instead of using Kinesis Firehose in the S3 database, is we used the serverless computing service, Amazon Lambda, to send the data to a virtual server, where it is then stored and dashboarded. So as I said, throughout the course of the project, a lot of the methodology had to be changed in order to tailor these services to our needs. The first thing, we actually replaced that S3 bucket with an Amazon relational database. Found out that didn't work very well either for this type of data, and scrapped that, and ended up using InfluxDB, which is more tailored to be used for IoT and time series applications. So instead of using a timestamp like we did before, this is again the IoT broker. We added a client ID here, which is very important for the organization of data when you're getting them from a variety of different sources. And it also helps control security, because you know if you're getting bad data, you can identify exactly which microcontroller it's coming from. Instead of using Kinesis Firehose, as I said, we're invoking a Lambda function that's responsible for sending the data to that virtual server. Now this is that Lambda function that I'm talking about. So as you can see, the data comes in here through Amazon IoT. Because we're hosting a third-party database, we ended up needing to use this new method of transmission. The first thing that the function does is parse through the data that's being sent through and ensures that it's being sent in the correct format to be used with the database. The next thing it does is send the data over HTTPS to the virtual server, which is a standard and secure protocol for sending data via web traffic. Now, the bottom picture here is the revised data format that you see. We added that client ID, the label for the type of measurement, and then the actual value of the measurement itself. So here we have some of the results. This is an environmental monitor. I pretty much just put this on my boss's desk and let it run for a few days. So as you can see, it's measuring temperature, humidity, CO2, total volatile organic compounds, and both small and large particle count. All this data has been securely transmitted all the way from that microcontroller to this dashboard that can be accessed from any web-enabled device. So some of the interesting things that we saw is around 4 a.m., there's that little temperature drop. We found out that that's when they're cutting off the HVAC system at night, and the cooler temperatures means that it cools down really quickly. And around 6 a.m., you can see the small particle count and the large particle count go up very high. This is because all of those HVAC systems were turning back on, and all that dust was getting kicked in the air. And this might not seem like something too impactful. However, like I said, if you were using this in a sanitized lab, it would be very important to know that all these particles are blowing around when everyone gets into work in the morning. On the bottom here, you can see the sharp drop in the CO2 and the total volatile organic compounds. This we found out was because it long time for these two sensors to self-calibrate, and that's all you're seeing here. That sharp drop is it going from the calibration mode to actually getting the correct values. On the top left here, you have the real-time values for temperature, humidity, ECO2, and TVOC. And as I said, this is only one possible implementation of the network. The important thing to focus on here is the fact that it is securely transmitted from the microcontroller to this dashboard. So this example is data collection, but it's also possible to use a control system using the same network. For example, a dashboard like this could be used in conjunction with an RFID scanner, where only a certain person can have access to a resource at a time. You could have a type of dashboard like this display the person's name or how many times per day that resource is accessed, and any type of time series data that you would like to see. This is another example. It's a little visually simpler. This is a distance sensor that was hooked up to that ESP32. Part of the reason we used the distance sensor is we wanted to see exactly how quickly we would be able to update the device data through the cloud so we could test the limitations of the system. So in this implementation, we found that at the very quickest, it would update about every 5 seconds, which is a very useful data point to have. We found out that for some real-time applications, it may be useful. If you want to know the status of something every minute, every 30 seconds, or 10 seconds, it would be very useful. But maybe for something that has to be updated 100 times a second, you wouldn't want to use these cloud capabilities. Now, in order to analyze whether or not this would be feasible to use for a company in the long term, we had to analyze the cost. So for the virtual server, a single instance is 1.3 cents per hour. IoT Core is only 8 cents for 1 million minutes of connection, which is about 2 years. Lambda is free for 1 million requests and 20 cents per million after. And both Influx and Grafana, the database and the dashboarding service, are free, where we would have had to pay for the Amazon services that we used before. Now, it is important to note that all these costs seem extremely low. However, if you had, let's say, 1,000 sensors deployed, all of these would add up very quickly. So, for example, if you had 2 sensors, it would be 8 cents per 500,000 minutes of connection. So the more you have, the more quickly the cost rises. Now I'll touch on the actual analysis and the real focus of this project, the security. So the purpose of this system was to show the feasibility of a network to be able to securely send data from this IoT device through the cloud. This network was essentially a test bed that was used to validate the abilities and limitations of a cloud-based data collection system. The first site of analysis in this project is the data collection system itself, including the microcontroller and the sensors. Without any security in this layer, we wouldn't be able to be sure that any individual node or any individual microcontroller had not been compromised. So there are 2 features that we use here to ensure security. The first is called flash encryption. What this does is it encrypts the contents of the attached SPI flash. Essentially, that's the main method of storing data for the microcontroller. It's encrypted with a standard AES 256-bit encryption key. The second method that we use is secure boot. This ensures that only the original user's code can be run on startup. So the data that's loaded from the flash on boot each time is verified by a key that's stored internal to the microcontroller on eFuses. So it actually has a code that's burned into the microcontroller, protected from software access, and essentially you aren't able to read it as a third party. So it's the responsibility of each user to ensure that they keep this private key safe. And the next site of analysis is the transfer of data between services. So generally, the transfer between, let's say, the microcontroller or the cloud, or the transfer we have between Amazon Web Services and the virtual server are where a security vulnerability is most likely to happen. So, as I said, the data collected by the microcontroller is sent to the cloud via MQTT. MQTT in this implementation uses transport layer security, and this ensures the confidentiality of the data as well as device authentication so that you know you're getting it from the correct source. It includes an X509 certificate and that standard encryption. And this type of protocol is not only standard for our method of data transmission, but nearly all secure web traffic. So any kind of e-commerce or online banking or secure web traffic in general uses these protocols. So we relied on them in the same way that many of these other services do, ensuring that all of this, the encryption and the authentication of devices would be ensured. Next, the data is handled by Amazon Web Services. And Amazon Web Services takes an interesting approach to data security. So they always guarantee security of the cloud. You know that when you're buying your processing power or whatever service you use, the servers that those are hosted on will be protected in their database facilities. However, in certain instances, Amazon says that the user has to implement the security inside of the cloud themselves. So for one portion of our system, where the data is being transferred from the IoT broker to that serverless computing service, Amazon guarantees that that data will stay safe. Now, in order to kind of gauge exactly how much you can trust that guarantee, we looked at some of the other companies that use this. So both Netflix, Spotify, Airbnb, and a lot of big companies that obviously have a much larger scale and focus of security rely on these guarantees in order to run their services. And we felt that as a small network, it would be safe for us to do as well. However, when we transfer data to those third-party services, as I said before, we cannot rely on that guarantee that's given by AWS because we are using those third-party implementations. So what we did here is we use HTTPS. This uses all the same protocols of transport layer security that MQTT does. And as I said before, it's a standard practice for secure web traffic, e-commerce, and online banking. So in the final results, we found that this network worked as a proof of concept to configure these ESP32 devices to send data through the cloud. The physical data security is protected from tampering by the secure boot and flash encryption. The protocols used between services are standard to secure web traffic and are safe to be trusted. We ensured that all the protocols that we're using are optimal for IoT implementations and require low compute power and low power consumption. This implementation can also be used to send alerts via email or text through Amazon Web Services, and we enable that real-time visualization of data. So, in the future, there are three main things that I think should be done with this project. The first is proper autonomous scalability. Because we use this network as a test bed, there wasn't really any point in deploying thousands of sensors. We just used a handful and tested the security of those. However, in the case of NASA Langley, if a bunch of people are coming to you and asking to have these sensors for whatever applications they want, you should be able to just plug it in and automatically give that user the credentials they need to read and analyze that data without having to have a network administrator sit there all day and partition these devices out, because it's a very time-consuming thing to do for individual devices. The second is compliance. So whether or not we're talking the application at NASA Langley, pretty much any organization has some focus on a basic level of data security. So we have to be able to prove that this device would work just as well as any other method of data security that they might use. And the last is continual security testing. So it's very easy to say that for a singular device, we are able to secure it end-to-end with encryption and verification. However, a lot of new issues are introduced when you have a wide fleet of devices that are coming out, whether or not it's a malicious insider or nodes going offline. It's just a lot more complex if you have 1,000 devices instead of one. So So in order to ensure that these devices stay safe, it's very important to be able to constantly monitor them and update and make sure that you're getting proper data from proper sources and that you don't have any malicious insiders that are able to compromise the security of the network as a whole. So this concludes my brief. Are there any questions?